Cooking is an analog process and has been for centuries. Most foods are cooked using an oven, stovetop, or over an open flame. But here, we explore a new heating technique: laser cooking. But can food be cooked on the inside using lasers? We use chicken as a model food system. We pureed the raw chicken in a food processor and extruded it using our 3D food printer. Current cooking techniques don't provide high spatial resolution, but we need high precision to properly cook 3D printed foods. We demonstrate the ability to cook foods at a millimeter scale with 3 different types of lasers: a blue laser operating at 445 nanometers, a near-infrared laser operating at 980 nanometers, and a mid-infrared laser operating at 10.6 microns. We use the cooking pattern that can be easily adjusted to optimize the heating conditions for chicken. By tuning parameters such as circle diameter, circle density, path length, randomness, and laser speed, we can optimize the distribution of energy that hits the surface of the food with higher resolution than conventional heating methods. We can even create checkerboard or more complex lace heating patterns that are not possible with conventional cooking. Unlike convection heating in an oven, laser broiling provides pulsed heating as it propagates across the surface of the food. There's an implicit trade-off between speed and amplitude of the energy pulse, which is only limited by the total power of the laser. By varying the number of passes of the laser from 4 passes to 1 continuous pass, we can compare real-time temperature with maximum recorded temperature and deduce the heating efficiency of different cooking patterns. Compared to oven broiling, we found that laser-cooked foods are more moist and shrink less after heating. Energy from visible and near-infrared lasers also pass through clear plastic mediums, giving us the ability to cook and brown foods within their original packaging. Most importantly, we found that different wavelengths of light can cook foods to different depths. In other words, blue lasers are better for penetrative cooking, while infrared lasers are best for browning. Multiple laser wavelengths should be combined for best cooking results. In the end, laser-cooked samples were edible and achieved food-safe temperatures for consumption. This technology is the first step in digitizing the cooking process and is poised to change the way we cook and think about foods.